Alright. So this is called Epsilon substitution. Now you've got your graph here. Look at it, it's all graphy. And it's got this little symbol that looks like a weird 3. So this is called epsilon. In automata, this essentially means nothing. It's just a substitution for a value that doesn't technically exist. Wrap your head around that. So, epsilon substitution, that's essentially saying draw this graph, draw this automata, draw this language without the epsilons. Now, how do we do that? You ask. That is a very good question, my friend. Now, as you can see, you've got other values. You've got 0 and 1 in this case, and you have 3 states: Q0, Q1, and Q2, Q2 being final, and Q0 being your initial state. I always forget the little arrow. So what we got to do first is we got to draw a little graph. I've gotten ahead of myself there. It's so exciting. And what we need to do is we need to show the transitions. Now, as we can see, from Q0 using value or transition 0, I can get to Q1. So I'm going to write that in, Q1. Wow, amazing. Now, using value 0, I can also travel via starting point Q0. Using value 0, I can travel to Q2. Wow, so I'm going to do comma Q2, and that's my set. Look how I do little brackets inside, not parentheses, but brackets. Wow. Now, using value 1 at Q0, I don't have anything, nothing at all. So I'm just going to put thigh there. Now, using Q1, which is here, using value 0, I can't travel anywhere. That's unfortunate. So I put thigh there. But using value 1, I can travel from Q1 to Q2. Handwriting's not that bad. And that's the whole thing, so I don't have to have that's my entire set right there. Now from Q2, I can't travel anywhere using either 0 or 1. So I've got thigh there and thigh there. What I can do is I can travel via epsilon. So that's fine. What I need to do is I need to draw the epsilon. You know, actually I'm going to cross that out. I'm going to draw epsilon in red. Just so it makes the better effect. Now, using Q2, traveling along epsilon, I can travel back 1 to Q1. That's good. So I travel to Q1. That's great. But now I've got to work my way back. So if I travel via Q2 to epsilon, then I should be able to travel via Q1. That's fine. So Q1, travel epsilon, that takes me to Q0. That's quite a little nifty thing. I've just done a complete loop. Now, that's my entire set for epsilon. I travel 1 space via epsilon, and it takes me back 1. Now I can't do that with Q0, so I put thigh there. But you may notice there's another column right there. That is for a little thing called epsilon star. Now, star within automata, that essentially means any arbitrary value, any arbitrary number of these transitions, any number of times, including 0, right? So if I do, again with the red, got to remember my color coding. If I do epsilon star, and I go to Q2, like I do here, now I can travel 1 epsilon, and that takes me to Q1. That's lucky, that's fine, but I already knew that. But with epsilon star, that's any number of epsilons, including 0, but greater than that. That's an infinite number of epsilons. I can travel, if there are an infinite number of epsilons along here, I can travel an infinite number of times. As many epsilons I can put that down there. So I travel 1, 2 epsilons, and that takes me to Q0. And that's a whole new set I've got right about there. And I can do this now. If I do Q star with Q1, epsilon star with Q1, that still takes me to 0, and I don't really have to change anything there. And with Q0, once again, nothing. That's thigh. That's simple enough. But we've still got our graph here. Now what we need to do is we need to convert this graph into a brand new one, and I am going to do that via, a little thing I like to call magic. Wow, it's amazing, it's appeared. That's right. He's a nerd and a wizard. Harry Potter, eat your heart out. So, what we're about to do is, you notice this new column I've drawn here and separated quite nicely. That has no epsilons, so that's fine. It's epsilon substitution, that's what's supposed to happen. However, if we're going to keep the same language, we have to abide by the same rules as this. Q2 must be able to travel to Q1 and travel to Q0. We have to conserve this. So what we do? Well, epsilon is a null value. We can't have it directly working like that. What we can do, however, is we can have it traveling along this, and then here. It's a magical little thing, right? Q2 can travel to Q1 using weight 0 by doing a long way jump here. But we just substitute these epsilons by saying it jumps directly to here, like a little shortcut. Now how we do this? Well, we simply write out our sets. Now you remember Q0 didn't change much, so I'm going to just go ahead and write that for you. Q1 bracket Q2, that's the full set, and it couldn't travel anywhere via 1. That's that. Now Q1, that's by itself. It couldn't travel anywhere using weight 0 before, but now what it can do is it can travel back to itself using weight 0 by going epsilon 0, epsilon 0. That's pretty nifty. Yeah, that's pretty cool. So now Q1 travels to itself. That's good. I've got a little loop going on. And Q1 travels to Q2 just like it normally did. Q2. Good so far. Now Q2 couldn't travel anywhere before. That's very disappointing, very sad. But using epsilon, it can travel to Q1 using weight 0. So I'm going to put in Q1 right there. That's great. But it can't really travel anywhere else other than itself. So I'm going to put in Q2 right there, because travels there. Now you might be asking, why don't I have Q0 here? And that's a fair question. It's a very good question. You don't have Q0 on this part of the graph. And the reason for that is Q2 cannot travel to itself using epsilon to Q0. It can travel to itself using weight 1, and it can travel to itself using weight 0. I forgot to write that, didn't I? Q0, Q2, there we go. Using weight 0 by going epsilon, epsilon, loop. It has a little loop right there. And it can travel back to Q1 using weight 0, 0, epsilon, epsilon, loop. It's quite a little nifty, but Q2 could never directly travel to Q1 while conserving the language. In order to conserve the language, there cannot be a direct link from this to this. So now I'm just going to quickly draw everything out in accordance to the language. Now I'm going to show you how to do this, and I apologize if this is very awkward. I know, God knows it is for me. So I've got Q0, that's my initial state. I'm not going to forget it this time. And I'm going to have Q1. I'm going to have oh God, why do I have to write it? It's tiny. Q2 with a big circle around it, which is unproportional. So I've got my regular lines I had. Which was weight. And I had to drop my pen, didn't I? had weight 0, had weight 1, and had weight 0. That's all fine. I've conserved the graph to quite a fair extent, but I need to adjust for the new graph. Now in this new graph, Q1 connects to itself via weight 0. Now the way I do this, little loop. Just going to save time for myself, leave these uncapped. It loops to itself via weight 0. That's fine. I've just conserved this loop right there. It's pretty good. Now Q2 could also travel to itself using weight 1. So I'm going to just do that. Using weight 1. And it could also loop to itself using weight 0. So I'm going to have that there as well. 0. Now, am I missing anything else? I do not believe so. Because epsilon, all the epsilons are conserved. The epsilons for Q2, the epsilons for Q1, and we never had any epsilons for Q0, so that's all conserved. I have now converted this graph into an equivalent graph with no epsilons in it, and I've completely substituted them as such. Now you may be asked to convert this into a regular expression, and now that is fine because I've already written it down. Notice I did it on the last videos back because recycling is good for you. This right here is how you confront it. This is called a concatenation, in which the language of A and the language of B are merged. You could see you have to travel along A and you have to travel along B. So when you represent this in a shortened version, you have A, B. Now if you're converting this entire graph into a smaller one, you convert it into Q1, Q1, Q2, Q3. But if you're doing a regular expression, you simply have A, B. Now if you have this, you're given an option between A and B. So you have A plus B, A or B. It's pretty simple, and the same rule applies. Now this is interesting. Now you have an A loop, A infinitely, right? So the way you represent this is through star. You can think of it as star being the letter or something for infinite, because you can run A infinitely along this line, followed by the concatenation of B. You can do infinitely number of A's, including 0, which is where epsilon comes in, because this would be technically you technically have something in the middle. Let's call it Z. That's a weird Z. Let's call it squivel, which would be epsilon. A. That's upside down for you. A would be epsilon A. And from school would you transfer B right there. This is the actual version without epsilon substitutions. This is the version with epsilon substitutions. You can then convert these statements into a regular expression for this as a whole. For example, at the end for Q2, you'd have to have an A star, and you'd have to have along here, you have an option of 0 star, because you can travel along this infinitely a number of times, and along here and then there infinite number of times, or 0, 1. So this would be written as 0 star plus 0, 1. Or if for some reason you had a loop carrying here, for example there, then it would be 0 star, that's a plus, that should be a plus, or 0 star, 1 star. And you could have that in a bracket and then work out the rest of your graph. So that's essentially all you have to do. Till next time, do your revision.